Good evening, everybody. At least good evening to the ones who are in Europe. Good day to everybody else in the world, or good morning, wherever you may be, to the fourth episode of the Nova Insights. No, it's the third episode of the Nova Insights. Sorry. To those who haven't been with us in the last two shows, my name is Till Gottbrat. I am working for Nova as a freelancer, doing the public relations. I take care for the Nova Pilots team and work a bit on Facebook and YouTube. And I have the honor to be the presenter for the Nova Insights. Those who haven't been with us, the Nova Insights was an idea which we introduced due to Corona. Like there's no live lectures. Many of us are not allowed to fly as we would like to be. Sites are closed. So we had the idea of sharing the experiences and the knowledge and the expertise of people who work at Nova and from some of the Nova Pilots team among the community, and it has been quite well received so far. This show will take approximately 30 minutes, 45 minutes, depending, and then you can answer questions. You can answer questions anytime, and we will be happy to answer them as good as we can. The last two shows, we couldn't answer all of the questions, but we tried to take care that you can get your answers afterwards. One of the main questions is it possible to watch this Nova Insights again later? Yes, it will be under the same link on YouTube. So no worries if you don't have the time to see the full show. You can watch it later again. Well, so that's now today, number 3. We are talking to Philipp Medicus, called Pippo, who is the head of R&D at Nova. And Pippo will talk about synergies and contrasts in paraglider design. And he looks at 3 completely different wings. It's the two-liner XENON, high aspect ratio, two-liner, very competitive. He looks at the PRION, which is a school wing. And then he looks at the GLITCH, which is at the moment Theo de Blick's acro wing, which Pippo designed especially for him. So he checks, what do they have these wings in common, and what's the complete difference between them? But before we start, Pippo, please introduce yourself. How long have you been with Nova? What are you doing? What's your...
Thanks, Till, for starting the introduction already. It's not so easy to define since when I'm with Nova, since it started very slowly. Besides my studies, I started as a freelancer for Nova doing different things. And it's about 10 years since I'm with Nova as a full-time employee in the R&D development.
And you studied what?
Mechanical engineering.
Okay. One quick question before you go into details. It was January 2020 when Theo de Blick joined Nova, which was kind of a new step for Nova, because there was this young boy in the acro world, which was completely new reasonably new for Nova. How do you work with him?
I will talk about that quite extensively later in my presentation. So it depends on the project. Obviously, his impact on the glitch was very big. His impact on the XENON was still significant, but a bit smaller, and his impact on the PRION was actually non-existent, as he was not involved in the development of the PRION. We mainly work via distance, which is not so complicated anymore, as Theo can share his test flights almost in real time. But yeah, I will talk about that actually when I talk about the development of the glitch.
Okay, but it was you who developed it, or was it that Theo came and brought his old favorite wing and say, hey, copy this and change this, or was it Who did it?
No way I would commit if it was your second. No, but no need to. It was Theo who came to us with a certain idea how the wing should look. We already had built 2 semi-successful prototypes, acro prototypes. That was a side project for Fabi Gasteiger, our test pilot, who is a very enthusiastic acro pilot. And so we didn't completely start from scratch, but we started almost from scratch. I remember Theo being very enthusiastic and optimistic. We had actually very little time left because the acro season, which then did not start due to Corona, but we didn't know back then. Theo came to us, I think, in December. The acro season, I think, started 6 months later. And I remember Theo being super confident that we would easily manage to build an acro wing within 6 months. And I felt quite some pressure, but it turned out to work, even if the competition season didn't start, but we would have been in time.
Okay. Well, so enough introduction. Once again, to our spectators, if you want to ask questions, please click on at the bottom somewhere. You can click on live chat, and then there will be an open field where you can enter your questions, and we will try to take care for them. Please take advantage of being able to talk directly to people. And now I hand over to your presentation, and you start your PowerPoint and everything, and we'll be excited to see what you tell us.
All right. So, like Till already said, I would like to talk about 3 quite different wings, which we all developed during the last 12 months. As already mentioned, that's our X-Alps 2-liner, which we certified a bit more than a month ago. The XENON, the school or training glider, which we certified in the same time frame, the PRION 5, and the acro glider, the GLITCH, which we won't ever certify. I'd like to start with the development of the XENON. Every development starts with a specification sheet. Here I show a very short version of that specification sheet. So the first 2 issues are obvious. The wing needs to be light, and the wing needs to be very performant. That's a very interesting combination from the development point of view, because the goal is not as light as possible, but the goal is rather as light as possible without sacrificing too much performance. So you have to very carefully think about what you need to achieve the performance and where it's better to save weight. One example for that is we have more than half a kilogram, more than 500 grams of nitinol rods inside the XENON, because in this case, we think that the advantages in terms of performance and stability outweigh the disadvantage of this 500 something gram more weight. Obviously, we wanted an END certification because that's required by the X-Alps rules. And we wanted to have a 2-liner because we think that the advantages are just overwhelming of this concept in this class. So based on those specifications, we start with a certain basic concept. By that, I mean, we start with a certain aspect ratio, we start with a certain cell count, with a certain line layout, because you have to start with something. And the first step, or one of the very first step, after this basic concept is finished, is the flow simulation. The airflow simulation is basically a virtual wind tunnel. You put an object, in our case a wing, inside that wind tunnel to understand its aerodynamic behavior. This picture, for example, shows the pressure distribution on the wing. So what you see in blue is a low pressure area. What you see in red is a high pressure area, which is...
May I just interrupt with one short question?
Of course.
Just to point it out. So your first step is to define the major things like the cell count, blah, 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 and so on. It's a two-liner. And then you design with the CAD program, you design the basic wing concept, like
Yes.
the virtual wing, and that virtual wing is put into a virtual wind tunnel.
Exactly.
That's basically right.
That's what happens, yes. And that doesn't mean that the aspect ratio and the cell count and all those parameters are defined forever. Actually, it's the opposite. All this airflow simulation and the other simulations I'm going to talk about, the aim of that is to find out the perfect aspect ratio, perfect cell count, perfect whatever, but you have to start with something. So there are many things you can see in this flow simulation. The pressure here, that's something best described as a frictional drag. You see that those dimples in between the ballooning cause quite some drag. Now I'm going to show you something which I assume most of you are not aware of. But it's something which is valid for every paraglider, which many of you might know is that the airflow, the closer to the tips you go, the more the airflow is deflected sideways. That's because of the wingtip vortex, which probably you all have heard of. The air is traveling from the bottom surface around the tip to the top surface. And that obviously deflects the airflow on the top surface the way I've shown here with that arrow. If I cut the wing along this line, what you basically see is the airfoil, how it is seen, so to say, by the airflow. Here again, the reason for this lateral airflow. And so what you see on bottom is the airfoil, how the air sees it, or more technical, how it is aerodynamically working, aerodynamically relevant. So you see the airfoil is actually heavily distorted because it has to travel above all those ballooning dimps and dimples. Yeah, that's basically valid for any paraglider, and there's not a lot you can do about it. I simplified the problem quite a bit. What is actually happening is that, like I already explained, on the bottom surface, the air is deflected towards the wingtip. On the top surface, it's deflected towards the center. So the actual airflow which the air sees is a bit more complex, but I thought that this simplification helps to understand this issue. Another kind of simplification I made is in our daily work with this tool. It's not so much about looking at colorful pictures. It's more about hard numbers. So this flow simulation provides hard data, like, for example, the lift of the wing, the drag of the wing, consequently the lift to drag ratio, which is the glide ratio basically, and a couple of other parameters like pitch stability and many more. And we use this data to compare all the different more than 100 virtual prototypes.
One quick interruption again, people. How close do you actually get if you look at the LD? How close do you get with your simulations to what the wing performs in, let's say, quiet early morning, 5 o'clock, quiet conditions? How many?
That's quite well. There are two aspects to this question. What we mainly care about actually is the relative accuracy. By relative accuracy, I mean that if I simulate two virtual prototypes and one ends up performing just a tiny bit more than the other, it's quite important that the very same will happen in real life. That's what I mean by relative accuracy or comparability. The absolute performance prediction is a lot more difficult to obtain, but also not so important. By absolute predictability, I mean the flow simulation data predicts a glide ratio of 1 to 10, and the wing in real life glides with exactly 1 to 10. There are many reasons why this is much more difficult to obtain. One obvious reason is the pilot's drag and the harness drag, which we don't care about. Not too much, at least. Or I don't care too much about it, because the wing design obviously has no effect on the pilot's drag. So there is no point in predicting the glide ratio with a harness and the pilot I know nothing about.
Yeah, there's one question that's closely related from Jürgen. He's asking why you don't direct the direction of the ribs according to the actual airflow, making it not like all parallel, but at the outer wing, more like this.
The reason that's a good question, which and the reason for that is actually the second arrow I drew here. You can easily, you can align the ribs according to the airflow on the bottom sail, or you can align it to the direction of the airflow, either on top sail or on bottom sail, but you can't do both. So the better you align it on top sail, the worse it is aligned on bottom sail, and vice versa. There is no way to align it both for both surfaces. Besides that, the direction of the amount of deflection changes with speed or angle of attack or lift. But the main reason is you would need the opposite on top and bottom, and you can't align the ribs on both those arrows.
It would be at least a big challenge to try to sew this.
I don't think the sewing. I don't think even the sewing is the problem, but I think it doesn't work. But if Jürgen has proper idea, feel free to send it. So what we use the flow simulation mainly is it's a optimization process. We can optimize the airflow, the airfoil. We can optimize the openings. We can optimize the curvature. We can optimize the ballooning. We can check, in case of the X-Alps wing, how much performance we could gain by adding 2 more cells or 5 more cells, and then judge if we think this performance gain is justified. So yeah, we can play around quite a bit. The main restriction of this flow simulation is that it does not consider any deformations of the glider. So the wing inside that virtual wind tunnel is just as rigid as a piece of rock. The simulation that also considers those deformations is called structure simulation. And that simulation knows that the glider isn't made out of rock, but out of actual ripstop fabric. So there is a material model, a physical material model behind that simulates quite well the behavior of the ripstop fabric we use. The screenshot here of the XENON is not too spectacular because that's already the result of a long optimization process, which obviously had the goal of reducing deformations. That's why I'm going to show you another screenshot of an ongoing development where you just see a lot more deformations, and where you, I think, see that this simulated wing behaves like an actual wing out of cloth. So the shape of the wrinkles and the dimples looks familiar. Yeah, the goal obviously is to minimize all those deformations. To summarize, what the things we simulate, because the things we can simulate is performance, speed, also obviously performance at different speeds, so polar curves. We can simulate the internal pressure. We can simulate the stability of a glider to a certain extent. And yeah, like I extensively explained, we can simulate deformations. What we can't simulate are all kind of maneuvers, starting from most simple ones like simple turns to complex ones like collapses. Sorry, we don't simulate turbulences. And we do not simulate production-related details. So that structure simulation here does not know that the cloth parts are sewed together. That is relevant because every sewing process leads to shrinkage, to a seam shrinkage. And the simulation doesn't know that. So in this simulation, the seam shrinkage is not existent. Because of all those reasons and a couple more, we need the flight tests of a prototype. Here you see the 3 pilots who I think were most involved in the flight tests of the XENON. On the very left, you see Tony Bender, who is changing some brake lines. I think this picture was taken in Bassano. By the way, Tony was also involved in the development of the original XENON, which happened around 30 years ago. In the center, you see Fabi Gasteiger. He has constantly pushing the development of the XENON throughout all those months. In this photo, he's literally pushing the speed bar to find out the stability limits of the XENON. This is a lucky shot taken from the passenger seat of a tandem. It was not an induced collapse. Fabi was really trying to find out at almost full bar in turbulent air when the XENON would collapse. Those kind of tests are obviously very valuable, because after 10 or 20 such collapses with the proto, you have a very good idea how the wing behaves in those real life conditions. And that's what Fabi was doing a lot. And also Theo on the very right. Theo was the reason why we even started with the X-Alps with the XENON development because he applied for X-Alps and needed a wing. And Theo was also heavily involved in the testing of the different prototypes. What those three were doing, in one short sentence, they gathered around 500 flights with the XENON prototypes that involved mainly thermal flying in different conditions. So in very turbulent air, to find out about the stability of the wing, in soft conditions to find out about the climb ability. It involved a lot of performance check in various conditions again. During the whole development, we had a wing, an X-Alps wing of one of our competitors, and which we flew quite a lot to find out how the XENON would behave in different conditions compared to that benchmark wing. And last but not least, the XENON testing also included the EN certification tests because we needed to pass the END tests. The difficult part about the testing is that sometimes it's quite difficult to find out if a certain modification leads to the intended result or not. So you change the trim of a glider and you want it to be more stable or to climb better. And that's really difficult to find out, and to have an acceptable degree of certainty. Sometimes you need 2 or 3 pilots trying just this one modification over and over to get a good impression. That's why so many flights are needed. So you see, simulation alone doesn't finish a glider or doesn't make a good glider. In the end, the XENON, like any other Nova glider, is the result of teamwork. In the end, I would like to show you a video of some collapses and tests with the XENON. I will start with a rather bad side collapse where Theo was twisted for a short moment, followed by more gentle ones. In the end, the certification was never really in danger, so we could focus on the handling, on the performance, on the real life aspects of this wing throughout the whole development.
People, there's one question from Elin, which is very closely related to what you have just shown. And it is, what about the landing characteristics of the XENON in small spaces? Like I mean, everybody has probably watched some of these spectacular landings on carpet-size landing spots surrounded by rocks, houses, and trees. And these guys just do it. And you told in the beginning that the landing and takeoff characteristics of the XENON are like a vital part because it is so important for the X-Alps. How can you simulate this, or is that clearly only the test pilots who do it? And how is actually the XENON in respect of landing and takeoff?
We don't simulate it. In theory, if we had if Airbus built paragliders with their BJ, they would certainly simulate it, but we don't. Of course, we have but on the other hand, that doesn't mean it's just try and error. We know from experience which parameters usually improve the takeoff or the landing behavior and which don't. So it's not try and error, but educated guessing, if you want. So we are with the launch and the landing behavior really happy. It there are many aspects to the landing behavior. There is, and also to what the X-Alps pilots are interested in. I think the most spectacular landing technique, which is quite famous on social media now, is this full speed uphill landing situation. I think but that's more from my personal flying perspective. I think what is just as important is the stall behavior, how easy, if you are not coming from below, but if you do a more classical top landing, and if you need to descend fast, there it's essential to have a very predictable stall behavior and not too sudden stall behavior. That's where the XENON is really good and easy to handle, I think. But yeah,
but just one more question related to the XENON. That's why I'm asking it now. It's from Raimund. He wants to know how difficult, how challenging it was for you and your team to develop your first two-liner. Like previously, all Nova wings that were sold were classic three-liner, four-liner concepts, and all of a sudden Theo comes in, hey guys, I want a two-liner, go for it.
Yeah, that's the outside view. The truth is that we have been building two-liner prototypes in the years before. The truth is also that we weren't really successful with it. I think that there are several reasons for that. One reason is that there was no real master plan with no deadline behind it. And when we started with the XENON development, there was an obvious deadline, and there was also an obvious specification sheet, because we said we need a X-Alps two-liner certified before, I think it was March 17th or whatever. And that led to huge enthusiasm in the team. And I think this enthusiasm helped to finish the wing. And I think we also had a bit of luck regarding the very first prototype. The first prototype was actually working just as good as I had hoped or dreamed for. So the first prototype was good enough for long and quite competitive cross-country flights, which I didn't really expect. So, and that gave us a head start. And and from there we didn't want to, there was no way we would let it go. So I think there are always a couple of factors which are needed for good development, and I think enthusiasm and consistency is certainly one of them. What we did before with the two-liners was when we started to struggle, we put the wing aside and thought, yeah, maybe we'll solve it later. When we were struggling during the XENON development, Fabi and me had some sleepless nights, and 1 week later, usually the problem was solved. That's, I think, why we succeeded relatively fast. But we weren't completely clueless regarding two-liners when we started, because we had built some already.
Okay, thanks.
So the next wing I'm going to talk about is the PRION. The specification sheet of the PRION obviously focuses a lot on the safety and the easy handling, which is most important for such a glider. The launch behavior needs to be easy as well. It needs a high level of pitch and roll damping. And obviously it needs an ENA certification. The very basic development workflow is the same as in case of the XENON. That means we do the very same simulation iterations before we start the first prototype. But I won't show you any of this in case of the PRION because I've already explained it. I rather want to show you some PRION specific development we did to make the handling of the wing as easy as possible. Those are three actually rather small details which still have a big impact. On the left, you see what we call adjustable brake handle. The idea of the advantage of the adjustable brake handle is that after launch, you don't need to change the grip of the brake handle. What you usually do is when you forward launch, you hold the brake handles like this, and then you wrap, and to have a more direct connection with the brake line. And for a trained pilot, that happens probably subconsciously, but for a beginner, that's an extra stress and demanding. And those adjustable brake handles really help to get rid of that. And they prevent beginners from learning to fly like this, which is very bad for many reasons. Second feature are lots of color marks on the risers. Some of you might think that those color-coded risers aren't really necessary. I think they make sense, and they are really standard in most parts of aviation. For example, in every glider plane, the handle for the air brake is blue. The handle for releasing the towing line is yellow. And it has been like this for, I don't know, 50 years. And this standardization really helps. I think it also, in a stressful situation, it also helps a really experienced pilot. That's why we use it. That's why we use those color codes, not just on the PRION. Something which I think is not beneficial for more experienced pilots is the brake travel indicator. That's a brake. You see that the brake line on the right has a green and yellow and then a red range. The red range is where the wing might start stalling or is about to stall. This brake travel indicator, on the one hand, helps the pilot to get a very rough idea of the usable brake range of the glider, but it even more helps the instructor to when giving commands. Most of you in school heard commands like pull brake handles to shoulder height or pull brake handles to breast height. And it's way more precise to have a command saying pull the brake handle until the yellow range or to the end of the yellow range or whatever. So the instructors can give the pilots the commands with more precision than they can do without that. Obviously, the flight tests of an ENA wing are just as important as of an X-Alps glider. The focus is just a very different one. In case of the PRION, we spent many days on the training hill, working and evaluating the launch and landing behavior. We did that with many pilots, even more than with the XENON, because in case of launching, everybody launches a bit different. And we had prototypes where two pilots didn't detect any flaws, but then there is a third or fourth pilot who consistently has problems because at launch, because he just does a tiny thing different. And that's why we tried to include many different pilots. And we also included instructors as well as the DHV to get a feedback from them. Obviously, we do a lot of maneuver tests. That's, I think, in the center picture, it's Ferdi Vogel doing a front collapse with the PRION. You also see Ferdi Vogel on the very right. He's not just a very successful cross-country pilot, but also an instructor. So he knows the instructor side of things as well, which is really helpful when developing a school glider. Also, Nikolaus Kurz, who is part of the development team, is an instructor. So we know a bit about the school side of things. And last but not least, we are flying the PRION a lot in thermals as well. That's mainly to judge the handling, to judge the stability, to judge the damping, but also to achieve a nice handling for efficient climbing. The video I'm going to show you is not a real development video because it was done after we finished the development, but still you kind of see what we focused on.
Can I just ask one short question in between?
Yes.
Which is from Christoph. He wants to know what explains passive safety from a structural perspective of a glider.
From a structural perspective.
I suppose he's talking about those details that you were showing on the XENON. I mean, what parameters make a wing safe?
I mean, my definition of passive safety would be how much the wing itself contributes to the safety without the pilot doing anything. And so my idea of passive safety is mainly related to collapse without or with little pilot or with wrong pilot input, and to launch, landing, whatever behavior. The structural side of things, I don't really understand it. Where structure plays a role is obviously in terms of load. So in terms of maximum load or load failure, which is almost non-issue in our sport, luckily. I don't fully understand the question. I'm sorry.
Maybe Christoph, maybe you can specify it more and ask the question again, and we pick it up later if it makes sense. And you show us your video, people.
Perfect. That's Theo launching the PRION mainly to demonstrate how easy it is without even touching the hands. Here he shows some standard tests. After a no-hand launch. The last wing I'm going to talk about is the GLITCH, which is a competition acro wing or a competition acro prototype. Yeah, like we already said in the very beginning, when Theo came to us, he obviously needed an acro prototype, and his specifications, he had a basic idea of how it should look like. For example, he wanted a certain aspect ratio of 5.8 because he thinks that's the sweet spot. And regarding the flying characteristics, I remember him saying, all you need to make sure is that the wing shoots and I will do the rest. So most important aspect of the flying characteristic was that the wing had to shoot. Yeah, like I said, we already had gathered some experience, maybe similar to the two-liner, which used to be a side project until we started the XENON. We also had an acro side project before we started the actual development of the glitch, before Theo joined us. And this was a side project of, yeah, basically me and Fabi Gasteiger, who is a very good acro pilot. I'm gonna show you another video of Fabi flying, I think, the second prototype, trying to do infinite tumbling. Yeah, and you see it wasn't working straight away. And Fabi was struggling quite a bit to get back to normal flight. Then Theo joined Nova, and this acro development turned from being a side project to being Theo's main project, which sped up things a lot. Theo was testing the prototypes in France mainly, and on some days he was doing 10 or more runs with different trim settings a day, and we were in constant contact to find out solutions to problems. So we were communicating via Messenger, and after each flight, Theo would send photos or videos with showing the problems, and together we tried to come up with solutions. It was a really fast forward development, mainly because, yeah, similar to the XENON, because Theo was super enthusiastic, and we also had a lot of pressure because Theo needed a competitive acro competition wing. It would have been really bad if we failed with this project and Theo would have to, I don't know, skip the acro competitions because we wouldn't have the wing. So, but this Theo's enthusiasm was quite infecting, and the workflow with him working in France turned out to be really efficient. So he would send, it's actually not in France, but still, he would send videos with some nasty collapses, and we would then together think of trim changes, how to fix it. And yeah, it were many, many iterations. And in the end, we succeeded. Here's another videos. The main thing we struggled with was actually the infinity tumbling. You see here a lot of collapses with different protos, different settings, and yeah, we were gradually improving. And that's the very latest version of the glitch, which super smoothly does all those shooting maneuvers. But in general, the impact of, in case of an acro pilot, in case of acro flying, I think the part the pilot contributes is way bigger than the part the wing contributes. So an acro pilot makes much more difference than an XC pilot, I would tend to say. So if you have the very best XC wing competing against a rather bad one, it's, I think, difficult to, if it's just too slow, it's difficult to win a task with that. With an acro wing, I think the pilot can make much more of a difference. And yeah, Theo obviously can. There is a very long 24-minute video on Theo's YouTube channel that goes into detail of the development of the glitch. I think it's really interesting to see, and when watching the video, you see how much work went into this wing. So the reason that we finished in, I think, just 3 months is not that it was so easy, but it was that Theo put so much work into finishing this glider. Now, I would like to talk about what all those wings have in common. There are some direct, maybe surprising similarities. One of them is all 3 airfoils. I showed the front part of all those 3 airfoils in the center of the screen. All those 3 airfoils have to work well at a high angle of attack for different reasons. The acro wing, people might be surprised that an acro wing works at a high angle of attack, or flies at a high angle of attack, but it does. So the reason acro wings are small are fast is because they are small, not because they are trimmed very fast. Actually, they are trimmed pretty slow in terms of the angle of attack. Otherwise, they would collapse during infinity tumbling, for example. The reason the XENON operates at a high angle of attack is because it's also rather small to provide good performance at high speed and to be able to fly fast. So when you're thermaling the XENON, you are doing it at a very high angle of attack, and the airfoil needs to be able to bear that high angle of attack. The PRION obviously is a rather small wing and therefore flying at a high angle of attack. So those 3 airfoils look very different, but still to the modifications you do on them for high angle of attack, for deep stall recovery, or for collapse resistance, they are, to a certain extent, they are similar. So it's 3 very different wings which have, in the end, fulfill some very similar tasks. I think much more important than those direct similarities is what I call indirect synergies. That's, first of all, the technology transfer. By that I mean the XENON, for example, challenged us to improve our simulation to have even more, to correspond the simulation results even better to reality than it was before. And those very same improvements, or the improvements we made for the XENON, are beneficial for all other wings because we use those very same simulation tools for all wings. The same is valid for production details. When we do certain optimizations to get a cleaner finish, for more performance, for better stall recovery, whatever, all our wings are going to benefit from that in the future.
A quick question.
Yeah.
You say that from top down, the XENON has positive effects on the lower category wings. Does it also work sometimes bottom up, that you learn something on a lower category wing, which also is useful for a higher class wing?
Yes, I wouldn't say it's too much related to the category. For example, we learned the double skin, our super lightweight wing, is a low category wing because it's ANA. And there we learned quite a bit about lightweight, which benefits the XENON. So that would be an example for bottom up. But obviously those simulation performance related things are more top down because there is simply more pressure on the XENON in terms of performance than on the PRION. But still, the PRION still benefits from an improved simulation workflow. Another synergy is the broader test know-how. That means when test pilots get experience with trimming those completely 3 different gliders to achieve a certain change in the flying characteristics, they will get a much deeper understanding of how things work and how things are related than if they only worked on 2-liners or if they only worked on acro gliders or whatever. And also for me as a designer, when I improve my understanding which airfoils or which line length or generally which parameters lead to the huge shooting which is required for the glitch, it helps me a lot to understand which parameters prevent the shooting which is needed for a training glider. So yeah, the view simply gets broader from the designer point of view and from the test pilot's point of view. And last but not least, the team synergies. We have a team with a lot of different strengths. We have acro pilots, XC pilots, hike and fly pilots. We have people with manufacturing expertise and with aerodynamic expertise. And that know-how is best used if we have lots of very different projects, because that way we can best learn from each other and improve. So yeah, if we only build a very narrow range of wings, we couldn't use all our knowledge the way we do it with this broader range. Yeah, that's the end of my presentation.
Okay.
I'm gonna stop my screen sharing, right?
Yeah.
Yeah.
We have quite a few questions being asked already, and I didn't want to interrupt you too much, and I try to group them a little bit together.
Sure.
One is obviously related to a very interesting topic, according to the desire for ultra lightweight wings for the X-Alps. I mean, also in many countries, cable cars and lifts don't work. So there, at least in the German-speaking part, we can see a huge boom in hike and fly, and everybody wants a lightweight wing. But of course, that means lighter fabrics, lighter constructions, lighter designs will always compromise on durability. How do you balance on this edge?
You don't have to balance in all aspects. For example, you have to balance more in case of a super ultralight glider where the goal is as light as possible, which is more valid for the double skin, for example, than for the XENON. I would say you have to balance more, because in case of the XENON, we used not the lightest possible material at the leading edge, for example, because we found that it's not just the durability that benefits from a bit heavier material, but also the performance, because the heavier material adds more stability at a part where it is most needed. So we did not, in case of the XENON, there was a bit less balance than in case of the double skin. But in the end, it's what we think is the pilot's demand that is decisive. If we think the pilot's demand is doing 500 flights on rocky launches, the wing is gonna look a lot different than if we think the main purpose is 200 flights on not so rocky launches and then selling the wing.
Yeah. Once again about the XENON. So you say it could be lighter slightly, but you're not opting to do this because of performance reasons and not so much of durability reasons. Is that right?
It's that's right, basically. Or they're using more general using heavier materials on some parts. I mean, the XENON is obviously a very light wing using mainly super light materials, but we didn't choose the super lightest materials everywhere because we thought that not only durability would improve, but also performance would improve.
Mm-hmm. Another question is directed towards how quickly can Nova build a new prototype? How long does it take? And how many prototypes do you typically need until a wing is ready for certification?
In theory, we could, if in a very best case scenario, we can build a prototype in 1 week. So that means if I finish a glider on Monday morning and send all the patterns, all the data which is needed for production to the factory, it could be finished on Friday. It also depends on how complex the wing is, obviously. So 2 weeks is what happens way more often than 1 week. So, but we calculate 2 weeks. And the amount of prototypes, there is it varies quite a bit. In case of the XENON, we built 5 prototypes, but we tried a lot on every prototype. So there are subversion. You can change quite a bit on the wing. You can obviously change all the lines, but you can also do some heavier changes with a pair of scissors and the repair tape. You can change quite a bit. And if we have, in case of a very bad prototype, it might be the case that it's just not worth to waste any time on it. But in case of the XENON, we thought that every prototype was good enough to get a lot of experience and to learn a lot from it and to try 10 or 20 different trim variants. So, but it was just 5 different physical wings, which we built, or different wings which we built before certification.
So that sounds like you were really lucky to be that fast, because I mean, I know from my own experience that sometimes it needs more prototypes. Obviously, it's always
Yes.
the first one. How good is it already? Like
Mm-hmm.
a lucky strike in the beginning, and then just fine tuning.
Mm-hmm.
And sometimes it needs much more work.
Mm-hmm. For the glitch, it was also 5 prototypes, but the glitch still is a prototype, so maybe there will be a 6th or 7th one. Yeah.
There's one question which is related to the topic complexity of wings. If you look back at the Phantom, the one who asked the question was talking about the experiment, which I think it isn't. How do you look at it now? And connected to this, I mean, the Phantom with 99 cells and more than 3,000 different parts that have to be carefully sewn together. what do you think will be the next chapter of wing manufacturing? Will you start gluing them, or will you use new fabrics like Dyneema laminated fabrics and stuff like that? So it's actually two questions. Start with the Phantom first.
With what was the question? What I think about the Phantom?
If you look back at the Phantom today, making this super complex wing, what was the benefits for Nova in the design process and wing performance, and what did you learn from it, and connected to this, what might be the next chapter in wing manufacturing in general?
What we learned from it is maybe related what I said just before. It broadens our view, because a 99 cell glider, the problems happen on very different spots than on a 35 cell glider. For example, the production becomes way more relevant. The production tolerances become more relevant because they might add up cell per cell. So from the production side, on the production side of things, we learned a lot, and also from if you do such drastic parameter changes, those are, if you want to call it an experiment, those are the experiments you learn a lot from. So if you build that's what I was explaining before. If you build a two-liner and an acro glider and a single skin wing and a school glider, and a Phantom, you maybe approach similar problems from very different angles and learn a lot. But that's a very general question. Specifically, I would say we learned a lot on the production side of things.
Will there be a Phantom 2? Are you working on it?
Yes, we are working on it, because the Phantom 1 was really successful. We are working on it since quite a while, actually, but we haven't succeeded in every aspect yet.
Okay. Then there's also a general question: which elements of a wing or which construction features give a high dampening? What makes a wing more damped? Or if somebody says this wing is very hard and kicking me while flying, what would you change? I mean, if I was a test pilot and say, hey, this thing is kicking my ass, what would you change to make it more comfy?
Yeah, I mean, there are many aspects to damping. I think the easiest to explain might be the pitch damping, the roll damping, and the jaw damping of the wing. That's mainly a matter of the airfoil used, of the curvature, of the line length of the glider, and also of the sweep. So how much the wingtips are bent backwards or forward. So generally, all those parameters, longer lines increase the damping because the angular amplitude gets smaller. Higher curvature decreases the roll damping. And
can you explain what exactly is the curvature?
By curvature, without explaining it exactly, but a wing with high curvature, by a wing with high curvature, I mean something which is bent down a lot. And a wing with low curvature, I would say, is something which is rather flat. And the flatter the wing is, the higher the roll damping. So, and besides those are the hard facts. Besides that, the kicking your ass, how you call it, aspect of a wing, that's also a lot related to the brakes. You would be surprised how much the brake geometry impacts your how you perceive the wing. So you can have one and the same wing with two different brakes, and with one brakes you will have the feel of an undamped wing, and with another brake settings you will have the feeling of a very soft wing. So that's quite subjective.
Okay, and then there is a pretty important question, a very general question, is the trim tolerance of a wing. Like how many millimeters or centimeters are the difference between optimum performance, optimum safety, optimum handling, flyable or even non-flyable and dangerous anymore?
Yeah, I mean the optimum is very narrow. What we want to ensure, obviously, is that the trim range where the safety is within what it should be is big enough.
Oh. I don't know whether we have a general technical problem. Well, I don't know whether it's just Pippo who has a technical issue and whether you can see me, but I think we are completely frozen. And I hope we can sort it out. Okay, I can read that you can still hear me, and only Pippo is frozen. So hopefully he comes back. Just to tell you a little bit about the trimming from my own experience is that I remember when Nova introduced the NTT, there were a lot of people who said that there is something, that Nova has a line problem, which was not the case. We only realized that the lines would lengthen or shrink within the first, let's say, 25 hours. So that's why we decided that the NTT, like a trim tuning, should be done very, very quickly, and to make sure that the wing performs as it should be. NTT stands for Nova Trim Tuning, and it's a computer-guided system to actually make sure that everybody who does a trim for Nova does it in the same way. Because otherwise, if you have people with a lot of experience, their trim might be, or the trim they perform on your wing might be quite good, but if you have somebody with less experience, it may be really, really poor. And repeatedly, there are issues just recently in Germany where obviously a wing was almost unflyable, which did not get the proper trim. So our recommendation is very clearly to do this NTT and do it very quickly. It's a little bit like on a wheel of a bicycle. If you buy a new bicycle and after a while you ride it, and then you should center your wheel and balance it properly. And once it's done properly, there are not so many changes anymore, unless you change your flying style, because it's the amount of force that goes into the lines actually has a big effect. A trimmer can, for example, see whether you prefer to turn right in thermals or left in thermals. So it makes a big difference. I hope Pippo comes back, because it's kind of strange to be the presenter and take over the whole lecture. Then there was one question about the brake travel indicator, the color gradient on the brake lines. Oh, I can see people is coming back.
Cool. Hi.
Ah, there he is again. Okay. I was trying to help you. Where were we stuck?
I forgot. I was struggling to come back.
Okay. There's one question related to a previous one is, how is passive safety affected by the design? I mean, one thing is very obviously that a low aspect ratio improves the passive safety. What other things makes a wing more safe in general?
Wow, that's very difficult to give a general answer to that. I mean, obviously, certain airfoils and certain curvatures, certain suspension positions lead to more passive safety. Also, I mean, increasing brake travel, but that's very. I mean, a wing with low speed will have more passive safety than one with higher speed. That's not necessarily helpful in stronger winds, but still, that's very difficult because it's the combination of many parameters. And even regarding the aspect ratio, I would say that there might be a sweet spot. So I would not say lower aspect ratio is safer down to aspect ratio 3. But it's just, I think it's too many parameters to give a general answer to that.
Okay. Then we have a couple of questions about the XENON, which is obviously a very interesting product, because I mean, that's shining and everybody's looking forward towards the X-Alps. By the way, we received questions, will the X-Alps be postponed? As far as I know, Zoom Productions will decide soon whether they will have to postpone it. But I mean, like everything that's related to Corona, it's very, very, very hard for them to tell people what will happen. Nobody knows. But it is an option that it might be postponed. But coming back to the XENON, how would you say is the performance of the XENON in relation to the benchmark similar wings?
We had so we like I said before, we had a benchmark glider which was successful at last X-Alps, so that reduces the possibility to 2 gliders. I won't reduce it. I won't reduce it even more, but we ended up having better performance than that benchmark wing, but there are a couple of interesting manufacturers who updated their last year's wings or released a new wing, which most of them haven't been flown besides any of the athletes, so it's gonna be difficult to say. But the feedback we got so far from very competitive and good pilots, one of them being Nico Donini, is very promising regarding the performance of the XENON. So I'm very confident that we will be super competitive with this glider.
So it's like there was the question is why end consumers would actually buy the XENON against others. I mean, if you were in a paragliding school and I'm a customer and I'm interested, so what would you say? Why should I try it? Why would I buy it? I mean, this performance is something mystic somehow.
I mean, handling isn't even more mystic because it's even difficult to measure. Well, I think the main design target, or we always obviously had an eye on the X-Alps, so it's a wing built for the X-Alps. But besides that, I think the XENON could be called an entry-level two-liner, if that word exists. So I think it's a very easy, approachable two-liner. It doesn't tend to behave nasty. It certainly doesn't have any of the problems the first generation two-liners used to have, like deep stall problems, frontal collapse problems, launch problems. So I think it's a very accessible wing. And the performance, the high-speed performance, the high-speed stability is also outstanding, I would say.
I know that in my flying club, or among my buddies, there's a couple of people who actually are pretty experienced and have been flying high C wings, or like three-liner D wings, and like, yeah, so many people are thinking, shall I step up to a two-liner? How experienced would you say does a pilot have to be to give it a try, at least?
I would say that the XENON isn't any bit more demanding than its aspect ratio suggests. So
which is how much?
It is 6.7. It's an aspect ratio of 6.7. I don't think a comparable three-liner, a similar three-liner with the same aspect ratio, would be any less demanding, because, like I said, I don't think that for a modern two-liner like the XENON, any of those two-liner problems which used to be there are still relevant. So I don't think, from my experience, there is nothing two-liner specific to be afraid of with this wing.
Mm-hmm. I think some of my friends will hear this with a lot of pleasure.
Yeah, but there are a lot of there are no two-liner specific problems, but there are a lot of two-liner specific benefits.
Okay.
Besides line drag and performance, it's mainly the B riser steering, which just works way better, and which leads in the end to being able to fly faster through turbulences. It's not just the B riser steering; it's also the higher stability of the two-liners. Yeah, but there are significant advantages.
So that, but also means that people will have to adapt their flying style, because it requires a different kind of, well, steering.
Yeah, I mean the B-liner steering is obviously restricted to two-liners, but I don't think it takes too long to adapt to it, especially if you have been doing some rear riser steering already. It feels more direct, and to some extent easier than the rear riser steering with the three-liner. So I really think like I said, it's a wing with aspect ratio 6.7. You have to be able to handle that aspect ratio, but besides that, it's easy. Maybe one of the main dangers is that it's so easy to fly, and it provides such a lot of stability that it's tempting to fly a lot faster through turbulent air, maybe close to the ground, than you would ever do with the three-liner. But that's in the end the responsibility of the pilot, and not nothing to blame the wing for.
Yeah, it's almost 1.5 hours already. Time is flying. So I would say that we asked the last question now, which is a very good one. And it's how affect the different materials of a lightweight, let's say on example, on the Ion 6 and the Ion 6 Lite. How does the lighter fabric affect the flying characteristics of the wing? Can people feel it with eyes closed, whether it's the normal wing or the lightweight, and what are the differences?
Yeah, the mass, the decreased mass of the wing is relevant. It's certainly feelable. If you decrease the wing's mass by 1 kilogram, that's from 5 to 4 kilo, that's 20%. Actually, it's just 10% because an equal amount of mass is the air inside the wing. So in terms of inertia, the wing is not 5 kilogram heavy, but 5 kilogram plus the air trapped inside. But there is still it's still a 10 or more % mass reduction, which you can feel. So the lightweight wing will be a bit more lively. It will impact the launch behavior. So it will, in very light wind, it will rise a bit easier. On the other hand, it might, if there's a bit more wind, it might be blown away from launch a bit easier. From my personal experience, because you said eyes closed, I think I'm when I fly a lightweight glider with the light cloth gives a lot more acoustic feedback than the heavier cloth, and I think sometimes for me it's a bit difficult to really differentiate in between that acoustic feedback and what is actually happening on the wing. So yeah, to me, I sometimes you hear on a lightweight wing, you hear deformations which you just hear because of the fabric, but you wouldn't hear the very same deformation on another wing. So that's something which might be misleading.
Okay, thanks a lot, people. Thanks to everybody who is watching. There's still open questions. Like there was one question whether Tony is still working on the Ion 6 Lite XXXS. Tony was sick for a while, so the project came to a little bit of a standstill. We are still pursuing it, and we hope that we can finish it soon. So that was the quick answer to the last question. I could answer it because I also know it.
Cool.
Thanks to everybody for watching us. We hope you enjoyed it. We hope you learned something. We hope you were entertained. And if you want to follow us in the future, please subscribe to our YouTube channel or follow us on Facebook or Instagram. There will be next week on Thursday again, there will be the next episode about flatland flying. Here you can see it. However, this will be in German. For us, it's a bit difficult because we have native German speakers, most of us. So we try to make everybody happy. I hope, yeah, you're not disappointed, but we might go on later with more English presentations. And if you have any questions, please feel free to ask them here in the chat or ask them on Facebook. We will try our best to answer them in time and answer them to your full satisfaction. And that's it for today. People, thanks again. Thanks to everybody who is watching. And see you maybe next week, or see you hopefully in real life, maybe at the X-Alps, at the turn point or whatever. All the best to you. Happy landings, great flights, and good night. Sleep well. Bye-bye.
Bye.